All right, so good morning to Mark, because in Berkeley it's 8 a.m. right now. Good evening to all of you and everything in between, to guys on Zoom who all count 32. Um, I must warn you from the very beginning that Mark is my mathematical father. I did a PhD with him in 1994 in Berkeley, so I apologize in advance that my introduction will be a little bit lengthy. But let's begin with Wikipedia data, because ChatGPT was again completely lying, so I had to just cross it out. So Mark was born on 22nd of December, 1937. But Mark, I'm really sorry to tell you, you are by far not the oldest speaker at Baby Steps. I think Roger Penrose beats you by a good 5 years. So
Oh, wow.
yeah. So no, you didn't make it to being the oldest one. Sorry. Roger is much older. Anyway, Mark did his PhD at Columbia University in 1963, which is before I was born. And his supervisor was Richard Caddison, a person who introduced operator algebras to the United States of America. And I remember when I organized, I think with Jonathan Rosenberg, 75th birthday conference for Mark in the Fields Institute in Toronto. Dick Caddison was one of our key invited speakers. And you know what Dick told me? He told me, you know what? It's a very strange feeling to give a talk at 75th birthday to your PhD student. So I still remember it. It was a very nice comment. Now, Mark's contributions to mathematics are enormous, and I'm not going to discuss all of them. Let me just give you some samples. So he introduced the concept of Morita equivalence as a fundamental notion in non-commutative geometry. He also unraveled so much about the rational rotation sister algebras. He introduced strict deformation quantization into the world of quantum groups. And more recently, and I believe his talk will end on this vein, he discovered a non-commutative analog of Gromov-Hausdorff convergence for compact metric spaces. You see, at a certain moment, Gromov had a brilliant idea of how to measure distances between metric spaces. It's not at all obvious how to do it, okay? And this is a very remarkable piece of mathematics that is used in particular for face recognition software, because you look at face as a metric space and you want to measure how far away they are. So when you enter Schengen area via a computer, this is Gromov-Hausdorff distance. And Mark did it in the world of non-commutative sister algebras. Okay, so that's enough Wikipedia style, okay. I also have it that in 2012, Mark was selected as one of the inaugural fellows of the American Mathematical Society. Okay, let's now stop Wikipedia. I want to tell you that when I came to Mark and asked him to become my supervisor, his answer flabbergasted me. I mean, he answered, okay, let's see what you can teach me. This is a very original answer. And, Mark is super famous in our environment for being the most pedantic person when it comes to the way you write mathematics. He subscribes to the policy, and now I completely agree with him. Maybe I wasn't so much in agreement when I was a student, but I definitely agree with him now, and I follow his footsteps. You see, Mark believes that when you write your PhD thesis, this is the last moment in your life when you can learn how to properly write mathematics. Okay, and he's probably the toughest person in the world when it comes to the clarity of what you write in mathematics. But this is a very fundamental skill, because the goal of publishing is to reach the audience, is to be understood. If you have even very brilliant ideas, but nobody understands them, they don't proliferate. So this is a very important thing. And I still remember that, okay, each time I would give a draft of my thesis to Mark, it would always come back with, the whole page being red with his markings, here is comma is missing here, this is wrong. But one thing which Mark found, and I found very sweet, I remember it after so many years, that he found a dangling participle in my thesis. This is a very subtle grammatical mistake which is obscure to native speakers, but I had the dangling participle in my thesis, which I remember to this day. But I really appreciate it, because you know, it is for life. I mean, it's a training that you get for life, that you really pay attention on how to write mathematics and how to be understood. And it's not just some, you know, simple grammar or linguistic errors. It's not the question of English. I remember when Marc was looking at my thesis and saying, Piotr, I read 2 sentences and I have learned nothing from these 2 sentences. You know, it should be economical, should be clear, and should be absolutely obvious what it is you are going to say. So because Marc is such a great supervisor, I have an enormous amount of siblings. I didn't check the count, but the body count, but it's like 30 people. I have 30 brothers and sisters from all over the world. Yeah. And your grandson, Marc, Mariusz, so my student, he's sitting here in the room. So that's a very, very big mathematical family. So of course you can understand why I'm so happy and delighted to have Marc here as our baby step speaker. And without any further ado, ladies and gentlemen, I'm giving you Marc Rieffel from UC Berkeley, who will tell us, who will explain to us what on earth is non-commutative geometry. Marc, the floor is yours. Take it away.
Thank you, Piotr, for that very generous introduction. And it's very good to see all of the people in the room and on Zoom, many of whom I understand are very early in their career and wondering what different topics there are that are exciting. And I'm very happy to have the opportunity to offer one of these topics, namely the topic of non-commutative geometry. So let me, oops, I have to, good. So non-commutative geometry is sometimes referred to as quantum geometry. And there is a reason for this, but also I think just one of the other reasons is that non-commutative is sort of a negative word, and also has more syllables than quantum. But quantum is also a word that's sprinkled around much too liberally in the literature. But I hope you will see from what I say that it's not inappropriate to use it in the setting I will describe. So since the word quantum is there, this certainly suggests that non-commutative geometry may be related to quantum physics in some way. And so let's look at classical physics, which is certainly related to ordinary geometry, as I think many of you have probably experienced at least a little bit. A classical physical system is modeled using its state space or phase space. There's not real consistency in the literature about some of the words that are used in this setting, but it's basically all of the possible states for the system that in other words, data that it can have. And just to make that more precise, if you have if your system is a rigid body in 3-dimensional space, then its state space would consist of all of the coordinates of all of the positions and of the velocities of its center of mass, together with all the angular coordinates and all the possible angular positions and velocities about its center of mass. And so in this case, and this frequently happens, the state space actually is a differentiable manifold, and you can have structure on that state space. But anyway, these it's basically all of the data that's needed in order to be able to predict how the system will evolve. In other words, how the states will evolve in time, given external forces and so on. And one can observe various properties of a classical system for example, its energy, and there are many more. And this, whatever the state that a system is in at a given moment, that determines the energy of the system at that moment. And so the energy can be viewed as a real valued function on the state space. So in general, in classical physics, the observables are modeled by functions on the state space. The state space usually has a topology, and the observables are usually continuous for that topology, but certainly other things can happen. And any continuous function on the state space can be considered to be an observable. Many of them will not be useful particularly, but that view can certainly be taken. And the functions, as you know, can be added and can be pointwise multiplied. And so the observables form an algebra. And this algebra is commutative. So this is relating the word commutative to the non-commutative in the title.
Sorry, may I have a question?
Yes.
So regarding the quantum case, do you really consider every self-adjoint operator as corresponding to some physical observable in quantum mechanics? This is a little bit philosophical question, but still, I'm interested in your opinion.
Well, in my opinion, you can certainly do that. It may not be useful to do that, but sure. I mean, in the most frequent or elementary setups, you can certainly, from a self-adjoint operator and the data of a state of a system, you can produce a real number. So you can say you've observed the system in that way.
Okay, thank you.
Okay, so I will go on. And so any actual laboratory equipment that you have for observing systems, they produce real numbers, but they will essentially always produce a bounded set of real numbers. I mean, you can quibble about that, but anyway, it's not unreasonable to restrict attention to bounded operators on the state space. And thus, if X is the state space, then the algebra of bounded observables is what I've noted here, C sub b of X, this standard notation, with its usual supremum norm. And in this context, probability measures on the state space X are also important and can be considered to be mixed states, as is the terminology that's often used, although, again, there are inconsistencies in the literature about this to some extent. But looking towards what we'll say about quantum mechanics, this set of probability measures can be denoted by S of X, and the elements of X itself can be viewed as point measures, so that the state space can be viewed as a subset of the set of probability measures. Now, experiments have been done whose results are interpreted as showing that in modeling quantum systems, it is essential to use complex numbers, not just real numbers. And I won't go into that. This is not particularly widely known, but if people want some references for it, I fairly recently posted a paper on the archive in which I happen to mention this and give a couple of references. So if this interests you, go look at my paper on the archive. But anyway, when modeling classical physical systems, it doesn't do any harm to view C sub b of x as consisting of complex valued functions and equipping it with its usual complex conjugation involution. And then the observables are simply going to be the self-adjoint elements in this algebra.
Sorry, Mark, I have a question. So
yes,
I wanted to ask why bounded functions and not instead like say that the state space is compact, for example, then everything is bounded, because that would be the other choice.
Well, because in many situations the state space is not bounded, and we will soon really be requiring that, but in general that the state space is not bounded, and that definitely causes technical complications.
Okay, thank you.
So anyway, the norm on this algebra again is just the supreme norm, but now on complex valued functions, and it satisfies this with quite innocent looking identity that I've just put up there that I think you can probably all work out in your heads. But what this means, but by definition, is that this algebra is a C-star algebra. I mean, I haven't given the definition of C-star algebra, but it basically, this is the key identity that, and I'll talk about that a little bit further. It's, of course, a commutative algebra, commutative C-star algebra. Now, as far as quantum systems go, physical quantum systems involving very small systems, atoms, molecules, and so on, they're experimentally, their behavior is weird and anti-intuitive. And one of the most basic experimental results is that certain pairs of observables are not simultaneously precisely observable. You can't know both the x-axis precise position of something and at the same time know it's a momentum in that direction. So that's just a very weird, anti-intuitive, experimental, basic experimental fact concerning quantum systems. And the only way that physicists have figured out for modeling quantum systems is weird, maybe necessarily so, but it has been very successful. And physicists have certainly tried all sorts of things for other methods, but the method I'm going to describe is the one that seems to be by far the most popular adapted and, as I say, very successful. And that is that there's no underlying space. The algebra of observables will be a so the algebra of observables, there will be an algebra of observables, and it is a closed subalgebra of the bounded operators on a Hilbert space over the complex numbers. And this subalgebra will be self-adjoint in the sense that if you have some element, little a in it, then that's an operator on this Hilbert space, then its adjoint operator also must be in the algebra. And then the observables themselves are modeled by the self-adjoint operators in the algebra. And exactly what happens is that two, let's say, physical observables will fail to be simultaneously observable exactly when the corresponding operators that model these observables do not commute. So the fact that one is looking at non-commutative algebras is exactly stems from this experimental fact that some pairs of observables are not simultaneously observable. And again, it's not difficult to check, but I won't. You may not be able to do it in your head, but easily on paper and pencil. The norm on the algebra of bounded operators on the Hilbert space satisfy that basically this same identity as I gave in the commutative case, but of course now applied to operators. And again, this means that by definition, one has a C-star algebra, now very possibly non-commutative. And the states of the system, and here again, this is slightly inconsistent with what we said earlier, but this is how the terminology is used. The states of the system are modeled by the positive linear functionals on the algebra. So if you have self-adjoint operators, you have a good definition of what it means for them to be positive, and so you look at positive linear functionals, in other words, that take positive operators to positive real numbers, and you want the ones of norm 1, and these are exactly the non-commutative analog of the probability measures on the state space X of a classical system. So you can see the slight, I mean, here we're using the word state for the probability measures in contrast to using state for, in the commutative case, for the original meaning. And the state space then is the collection of these states, and we'll denote it again by S of A, and it is a, well, okay, here I'm already haven't put down a hypothesis, but we'll assume that our algebra has an identity element, and in that case, the state space is a convex, weakly compact subset of the dual Banach space of the algebra A. So that in the quantum situation, there are often no points and points would be actually homomorphisms of the algebra into the complex numbers. Though their role often is taken by the extreme points of the state space, which are often called pure states. And again, there's confusion, some confusion in terminology between how the physicists talk about states and our mathematical conventions. But that once you are familiar with the language, it doesn't cause any problems. So the main message at the beginning here is that classical physics is modeled by commutative C-star algebras, whereas quantum physics is modeled by possibly non-commutative C-star algebras. So that's the first big message that I hope that those of you who are not familiar with all of this will take from my talk. And here I give the definition that an abstract C-star algebra, it's simply a Banach algebra over the, I should have said over the complex numbers, that has an involution, so it's a star algebra, and that satisfies this identity that I've been putting up. And yeah, okay, now for simplicity, we'll now always assume that our algebras have an identity element. So in contrast to the functions vanish, the algebra functions vanishing on the real line of, that doesn't have an identity element, but is still very appropriate for classical physics. And we'll say an algebra is unital if it has an identity. And we'll be interested in homomorphisms between unital algebras. And it will be said to be, a homomorphism will be said to be unital if it takes the identity element of the domain algebra to the identity element of the range algebra. And for any unital algebra A over complex numbers, we'll let delta sub A be the collection of unital homomorphisms from A into the complex numbers. And there easily cannot be any. Maybe at this point I should say, if your Hilbert space is happen in the quantum situation is finite dimensional, then the algebra of bounded operators on it is basically a full matrix algebra, and that's a fine and a very important example, simple example of a C-star algebra, and as for matrix algebras, they will have no unital homomorphisms into the complex numbers as soon as their dimension is at least 2. So, but going back to the case when X is a compact space, for each point X, let delta sub X be the functional on the algebra of continuous functions on X, consisting of evaluating functions at the point X. And so that with the notation I just introduced, delta sub X is an element of this capital delta sub X. And a basic theorem is that every element of capital delta sub A is evaluation at some point X. This is where my algebra A is C of X. That's not obvious, but all of you, I believe, have the mathematical background to, without too much difficulty, obtain find a proof of that theorem. If you haven't, probably many of you have not seen this fact, but anyway, it's not obvious, but it's a little. It involves basically a little compactness argument. You certainly need compactness for this to be true. So anyway, yeah, the state space is included in the original space X is included in this capital delta sub A, and in a well, no, I even more that you have a natural homeomorphism from X into capital delta sub A when oh, that's a typo. When delta sub A is equipped with the weak star topology. The point is that thus up to a natural homeomorphism, X with its topology can be recovered from the algebra C of X. And the result of this is that in principle, any structure on X will have an equivalent structure on the algebra C of X, from which it can be recovered. So there should be, in some sense, a bijection between structures on the compact space X and structures on C of X. By the way, all the topologies I'm mentioning are Hausdorff topologies. Just not bothering to say that. And the little Gelfand-Naimark theorem from 1943 says that any unital abstract commutative C-star algebras is naturally isomorphic to the unital C-star algebra C of this capital delta of A that I described, namely where that's all of the unital homomorphisms into the complex numbers. So every abstract commutative C-star algebra is isomorphic to a concrete C-star algebra, a C of X.
Mark, I have a silly question, if I may.
Yes.
Please correct me if I'm wrong, but I seem to remember that if you are speaking about the unital homomorphism into complex numbers, then it's automatically star preserving. Do I remember it correctly?
Yes.
Okay, thanks.
That's right. Yeah, that requires some argument, a little argument, but yeah. Yes. So from this we see that at least in principle, and this is a very, very useful point of view to take, the study of compact Hausdorff spaces is equivalent to the study of unital commutative C-star algebras. I mean, there's in fancy terminology, there's a contravariant equivalence of the categories of those two types of objects. But then there's the big Gelfand-Naimark theorem of the same year that says that any unital abstract C-star algebra, maybe not commutative, is isomorphic to a unital C-star subalgebra of the bounded operators on some Hilbert space H. However, in this case, in contrast to the commutative case, there's no uniqueness about what the representation is and what no uniqueness of the Hilbert space and so on. But this is a very fundamental theorem in the situation. So the whole idea of non-commutative geometry is then to think of possibly non-commutative unital C-star algebras as generalizations of the algebras of functions on compact spaces. And with that motivation, that idea in mind, one then tries to extend many aspects of the geometry on compact spaces to general unital C-star algebras. So this is the basic idea of non-commutative geometry. So again, you think of non-commutative C-star algebras as, in some sense, generalizations of the algebras of functions on compact spaces, which are your commutative C-star algebras. And then for many of the many aspects of geometry on compact spaces, you try to extend those to the setting of non-commutative unital C-star algebras. So, although he built on a tremendous amount of earlier work, all of the work done on developing operator algebras, C-star algebras, and so on. The first paper explicitly on non-commutative geometry was published in 1980 by Alain Kuhn, who's a field medalist for his slightly earlier work on operator algebras, and he has been the leader of the subject since that time. Still very active, and starting with his paper, the subject grew rapidly. Many people started working in this direction, and many connections with many other parts of mathematics and its applications, notably to physics, but very much to many applications that don't come out of physics. And in 1994, Kuhn published an amazing book called Non-Commutative Geometry, in which he provides a broad panorama of the state of the subject at that time. And this book is freely available for download from the web. And so for any of you who are curious about what the many applications were already known by 1994, I certainly encourage you to download the book and just browse a bit through it. You have to be careful not to get depressed, because the book draws on almost every area of mathematics. And
Marc, may I throw in a quick historical remark? I cannot
yes.
resist. So Alain got his Fields Medal at IMPAN in Warsaw in 1982. So we gave him a Fields Medal.
Yeah.
and if you would tilt your head a little bit, we could see the cover of a book you are talking about, because there is a piece of tapestry on your wall, and this is exactly the front cover of a book. This piece of tapestry on the wall is the front cover of a book.
It's a quilt that my wife made based on the front cover, which she gave to me as a surprise, very nice surprise. Okay, let's see. How am I doing on time? Okay, I guess I'm doing, I think, reasonably well.
We have officially 22 minutes left, but our dinner is half an hour later. So the absolute cutoff time is 18:30 our time, and now it's 17:38. So official time is still 22 minutes. Maximal time 52 minutes.
Well, it looks as though I'm about halfway through, so I'm not in too bad shape. Okay, so just the subject certainly is continued to expand rapidly from 1994, and it's still a very active field of research at the present time. Many very exciting developments taking place. But I do want to give you one example of the process of generalizing classical geometric structures on compact spaces to the non-commutative setting. I should say that there's no algorithm for finding such extensions, but there are a number of different approaches to it. But I'll give you one of the sort of more obvious approaches. So, namely, one path is to whatever geometrical structure you're trying to generalize, you try to express that structure entirely in terms of the if this is a structure on the space on a compact space X, you try to express it entirely in terms of the algebra C of x without mentioning points, and in a way that does not mention commutativity, and then you can just take that description and apply it directly to non-commutative C-star algebras. That is not always so easily done, but it can be done in quite a few situations, and can be very effective. So the most basic structure in geometry is that of a metric space. I mean, after all, the word geometry comes from metri, measuring, and geo meaning basically the earth. So it's measuring the earth, and it really means measuring the distances between points on a space, and that, of course, means that you're dealing with a metric space. So if that's our motivation, if that's the structure that we want to generalize, what is going to be a quantum metric space? How do we? So what we need to do is to express metrics, on a metric on a compact space entirely in terms of the algebra of functions on the space, and it's not particularly obvious how to do that. But if you have a compact metric space x comma d, and you know the algebra you want to use is C of x, then it's fairly well known. I mean, many of you have seen, at least in restricted contexts, that to each function on x, you can attach its Lipschitz constant that I describe here. And yeah, I should have put an L super D. It depends on the metric, but up on the second line here. So you simply, for a given function, you look at its value at two different points. You take the absolute value of the difference, and you divide by the metric, and you take the supremum of all those real numbers that you get, and that's going to be the Lipschitz constant. And often that supremum is infinite. If it's infinite, we say that the function is not a Lipschitz function. And I use this sort of script super D here for the functions for which the Lipschitz constant is finite. In other words, that's the set of Lipschitz functions. And this L super D satisfies a number of basic properties which often are not remarked upon when Lipschitz constants are used. But first of all, Lipschitz constant is zero exactly if the function is constant. So it's a constant multiple, complex multiple of the constant function 1. And L, again, I should have L super D, is a semi-norm as long as you extend the definition of semi-norm to allow the value plus infinity. And that is that for any f and g in the algebra, you have that L super D on the sum of f and g is less than or equal to, you can see the Lipschitz constant on f plus the Lipschitz constant on g, where if one or both of those quantities are equal to plus infinity, you know what the meaning of that is going to be. And furthermore, if f and g are in your algebra, then the Lipschitz function of their pointwise product satisfies a Leibniz type inequality that I've written down there for you. And as a consequence of this, the set of Lipschitz functions is a subalgebra of the algebra A. And if you take any function f, and we're using complex valued functions, and so the star just means complex conjugation, then L of d on the complex conjugate of a function is equal to L super d on the function. And so the Lipschitz functions form a star subalgebra. And the only item which requires some work is that the Lipschitz functions are norm dense in A, and that's basically uses you find you have enough of them that separate points, and then the Stone-Weierstrass theorem tells you that they will be norm dense. So you have all these these properties that are fairly easily understood. But there's one more property that's, it's going to be after this. Yeah, this semi-norm is it's not continuous in general with respect to the norm on the algebra, but it is lower semi-continuous with respect to that norm, whatever that means. Anyway, there's one more property that's important and an important fact, and that is that from the semi-norm L sub d, we can recover the metric d from this semi-norm by the formula that I've written down there. That I mean, again, this requires a bit of work, but it's not especially difficult to do. So it's very important that, I mean, this is key to what's going on here. The data consisting of the algebra L super A and its semi-norm L super D is equivalent to the data X comma D. From either one, you can get the other. You can go back. And so you see that in this way, we have succeeded in expressing the metric in terms just of the algebra and this semi-norm with no mention of points, and we never used commutativity of the algebra. So that we see, I mean, this suggests how we might define a non-commutative metric as being in terms of a semi-norm on the algebra allowed to take value plus infinity that satisfies the properties that I listed above. But there's one more property that this semi-norm has, and this is the less obvious property, but very important. So first of all, once one has the metric space and this semi-norm, we can use the semi-norm to define an ordinary metric on the set of probability measures on X. That is on S of A, and you can anticipate that this will be important in the quantum setting also. Simply, yeah, the distance between two probability measures is gotten by evaluating the two functionals on elements of, on functions. These are probability measures. Evaluating two probability measures on your functions, the ones of Lipschitz constant no bigger than 1. And that is easily seen to define a metric. And this metric is the same as the, well, this formula is basically just the restriction of the earlier form. I'm saying it backward. The restriction of this formula to the point measures gives us exactly the formula for recovering the metric. Let's see where that formula was. Yeah, the formula right there is just the formula I just gave you, but it restricted to point measures. So it's an important and unobvious theorem. I mean, this is the harder theorem to prove, due basically to Kantorovich back in the 1940s. Another, well, he was a Nobel Prize winner in economics, but that the topology on the state space gotten by using this metric on it coincides with the weak star topology on this state space, so that this state space with this metric is actually compact, because the state space for the weak star topology is going to be compact by Aloglu's theorem. So this may be getting beyond what some of you know, but anyway, this is important part of functional analysis that gives you this result.
Sorry, Mark, allow me to ask another silly question.
Yes.
So what happens if your X is a compact Hausdorff space, but it is a vicious one, not metrizable? So what happens with all this Lipschitz stuff? I know you assume here, but you have, okay, you cannot even formulate it. Okay.
Yeah.
You cannot even formulate it because in the metric.
No, because you have to have, yes, you have to have your metric, right?
Okay.
So all of this depends on your spaces being metrizable. That's true.
Okay.
No, but that's good to point out.
Yeah. Okay.
So here finally is the definition of a compact quantum metric space. You have a unital C-star algebra. You have its state space. And so by a C-star metric on this algebra, we mean a semi-norm on the algebra permitted to take the value plus infinity. And that satisfies the evident version of all of the 6 properties I listed earlier, the fairly obvious properties, and also has the property described just above, namely that when one uses this semi-norm to define a metric on the state space of your C-star algebra by the obvious version of the formula that I gave above, that then the topology on the state space from this metric coincides with the weak star topology, so that the state space with this metric is compact.
Wait a second. Let me get back now to my question, because now you have a definition which does not use the concept of a metric, because you kind of define it. So if I would, for starters, take A to be a commutative C-star algebra and a non-metrizable compact Hausdorff space, so one of these axioms would have to fail.
Yes, I think it's.
No, but Piotr, in this definition, you assume the existence of L.
Yeah.
Axiomatically.
But so that. fail, and L with such properties
Yeah.
would not exist.
I suspect it's that the Lipschitz functions would be dense,
Okay, you see?
but I'm Yeah.
That's because you put it, give it
yeah,
automatically.
yeah,
There is no concept of a
yes,
metric. Yeah.
right,
And simply these
exactly.
axioms have to fail. And
Yes.
yeah.
Yeah.
Okay, thanks. So now
Well,
I'm happy with my question.
or this property. I mean, it's very easy to get semi-norms that satisfy all of the other properties, but this axiom, this last axiom about
the topology, yes.
About the topology fails.
Exactly.
Just as a semi-norm, you can simply use the norm on the algebra.
Yeah.
I mean, that's a perfectly good semi-norm, and then this axiom will certainly fail unless the algebra is finite dimensional.
Yeah. Okay. Thank you so much. And now I'm happy with my question.
So, and by a compact C-star metric space will mean a pair A where A comma L where A is a unital C-star algebra and L is a C-star metric on A. And by now, many classes of compact metric spaces are known. I should say that Piotr mentioned this business of Gromov-Hausdorff distance, and that for the quantum version of that, this last axiom about the state space being compact for the metric that you get, that's crucial for making sense of the Gromov-Hausdorff distance, whatever that is, in this quantum setting. Anyway, so many examples are now known, and there are many different methods of construction, and usually the most difficult property to verify is this last one, concerning the compactness of the state space for the metric topology. There are a number of interesting candidates for which this last property, one can guess that it's true, but no one's been able to verify so far whether it's true or not. So I'll give you an example of one method of construction that yields lots of interesting examples. I guess I'm not doing so well on my time. Let G be a compact metrizable group and let L be a continuous length function on the group. So that's really thing thought of as a distance from points to the identity element of the group. And it's such that when you define a metric, well, D on the group by the little formula that I've given you here, then that gives you a metric on the group that's actually invariant under left translation.
Sorry,
And
could you explain what is the definition of this continuous length function, since you don't assume your group to be finitely generated, yes? So it is not like a word metric.
Well, but it satisfies the same properties. I mean, the basic property is that the length of a product of two group elements is less than or equal to the sum of the lengths of the two elements. Length meaning
Okay,
distance
so it
from
is
the identity element. Yeah. So, you want the L of an element to be 0 only if the element is the identity element. And,
just a stupid question, such a function always exists, yes? Or it is somehow restricted?
Yeah, but you can certainly always construct one. If you want them to be continuous on a topological group, things can get a little bit more complicated. And if your group is not metrizable,
so your group is compact metrizable. So it means that there is some metric which is compatible with the original topology, and then you consider this continuous length function. After considering this continuous length function, you have another metric, and do you assume that this metric corresponds with the gives the same topology as the original topology, or you don't assume it?
I certainly am assuming that you're getting this, that this comprises the topology. Yes.
Okay, okay, but this is an assumption. It's not automatic. Yes.
Yeah.
Okay, thank you.
Yeah. So anyway, and then if you let the group act as a group of automorphisms of a C-star algebra, so that means that you have alpha being a continuous homomorphism from G into the automorphism group of the C-star algebra, and you need a suitable continuity. And assume that the action is ergodic, meaning that the only elements of the algebra that are left fixed by this action are the scalar multiples of the identity, then you could define a semi-norm L on the algebra by the formula that I've given there. You just see how, for any element T of the group, you see how much it moves the element A, and you look at the distance it's been moved and divide by the length function. And it's a theorem that requires a little bit of work, that in this full generality, this semi-norm L will be a C-star metric on your algebra. So as examples, a very simple example, if you have a Hilbert space and a unitary representation U of that's irreducible of the your group, so it's going to be a finite dimensional Hilbert space, and if you let alpha be the action of the group defined just by conjugating by the unitary elements, this action is ergodic because of the assumption that the representation is irreducible. And then anytime you have a continuous length function on the group G, you obtain a C-star metric on the bounded operators on H, which of course is finite dimensional. It's a full matrix algebra, but this gives a whole lot of different constructions of different C-star metrics on full matrix algebras. So that's a finite dimensional situation, but one that turns out to be quite interesting.
So what goes wrong in the infinite dimensional case in this example?
Let's see. Let's see. I'm getting. Yeah, I think ergodicity. No.
Exactly. I think ergodicity fails.
Yeah. Yeah, I think.
Ergodicity is equivalent to the representation being irreducible. So maybe you restrict.
I think right. You don't have irreducible.
You
don't have irreducible representation. That's right.
Finite dimensional, yes. So for example, like for a compact group, yes.
Yes. Yeah, I'm assuming my group is compact.
Okay. Then it is automatically every irreducible is finite dimensional. Okay, so this is a property of group.
Yeah.
Okay.
Yes.
I see. Thank you.
Okay, so just to give one, this is the last piece as an infinite dimensional example. If you look at the Hilbert space L2 of R and you let U be the unitary operator defined just by multiplying by either the 2 pi I R, that function, one can show that the C-star algebra that generates is isomorphic to the continuous functions on the unit circle, let's say unit circle in the complex numbers. And on the other hand, if you take a real number theta and you let V be the unitary operator on H defined just by translating by theta, and if you look at Fourier transform, you can show again that the C star algebra that V generates is isomorphic to the functions on the circle. And if you let A theta be the C star algebra generated by U and V together, and if theta is an integer, then U and V commute, and one can show that the C star algebra is isomorphic to the functions on the two torus. Donut, if you want. But if theta is irrational, it's very interesting that one can show that A theta is actually a simple C star algebra in the sense it contains no proper ideal. I mean, it's highly non-commutative. Yeah, just as a comment for appropriate definitions, these A thetas can be shown to be deformation quantizations of the functions on the two torus. That hints at another way of constructing examples. And if you let your group be the two torus group and the action just be by the simple formulas that I've given up there, then you can show that this action is ergodic, and you have lots of continuous length functions on the torus group. And so in this way, one constructs many C star metrics on these algebra A thetas. These A thetas are often called non-commutative tori. So that's a very basic, important, relatively simple example for what I've been talking about. So I should end here.
Okay. Marc, thank you very, very much indeed.
Very much my pleasure.
So now, guys, do you know what non-commutative geometry is? Yes. Yes, Eva, bravo.
Thank you.
I have just one quick remark. You see that's this quantum torus, non-commutative torus, that's the irrational rotation C-star algebra I was referring to. And let me take this opportunity to mention one of the famous achievements of Marc. He were so-called powers Rieffel idempotents. I mean, when you look at the classical torus, this is a connected space. So when you look at the C-star algebra of continuous functions, it doesn't have any non-trivial idempotence because it's connected. Okay, so and when you have a C-star algebra with irrational rotation C-star algebra, it's a simple C-star algebra, and so it's like one big chunk. So it even looks, completely indivisible. And lo and behold, it turned out that it has non-trivial projections that even generate the non-trivial part of K theory. So this was quite a big surprise. Yeah. And these are named powers Rieffel idempotents. This was just a historical remark. Okay, now, any questions? Zoom as well. Guys on Zoom, if you want to ask a question, just ask it. Okay, Axel, go ahead.
Hello, thank you for this clear presentation. I was having a question about what does it really mean, this the geometry term in non-commutative geometry, because it seems to be like a very general term, non-commutative geometry, and I can understand with metric spaces and the example you gave that we can find some geometry, but I was wondering if how should we understand this word?
I'm not sure that I understand your question, but let me say motivation for all of this came in substantial part from work of Alain Kuhn himself, and he was looking at. I mean, I'm going to say a lot of words that probably most of you don't know very much about, but he was looking at differentiable manifolds, more specifically Riemannian manifolds, mostly compact ones, but not exclusively. And he was trying to figure out what an appropriate definition would be for a non-commutative Riemannian manifold, and he focused in on what was called the Dirac operator for a Riemannian manifold, and showed that I mean in quite complicated work that the Dirac operator basically, well, it satisfies quite a long list of axioms, which then he could show if you had a commutative algebra and Dirac an operator that satisfies these axioms, you got back the original manifold. But again, he could drop the requirement of commutativity and in fact drop many of the axioms and talk about Dirac operators in more general context. And in the process of doing that, using the Dirac operator, he did define a semi-norm that gave him a distance on the states of the non-commutative systems. So in other words, one can subsume in what I've been saying very much a theory of non-commutative Riemannian manifolds, which are a complicated, very important part of ordinary geometry. That's that in this case it's differential geometry. So that's an example. I don't know whether that answers your question, but
Yes, thank you. That answers my question. Thank you.
By the way, Axel, we'll have Nadia Larsen speaking about spectral triples, so this will be exactly the geometry. Go ahead. Microphone.
Yes, so one question to the first part of your presentation where you discussed how non-commutative geometry is related to quantum mechanics. So you mentioned there that elements of your algebras are bounded operators, but in standard quantum mechanics course, one learns very quickly that actually energy operator is not bounded, and you can see it by just considering a plane wave, and the details would depend on your domain, but let's assume that this is periodic that you have periodic boundary, and then you can take the plane wave in this direction, e to I k x, then energy would be proportional to the square of the wave vector k, and those functions.
Even at a more elementary level, the standard position, observable position in the x direction, is an unbounded operator.
Are you uninterested in energy be an element of your algebras, or am I missing something?
Well, from what you're saying, even position is not an element of my algebra, but you can consider an observable that gives you position up to a certain constant, and then just just gets cut off at that point, which again, if you are using instruments to measure things, I mean that will basically be what you are finding, but in the other direction, if you start with your algebra of bounded operators and look at subalgebras and so on, there are notions of what you mean by unbounded operators that are affiliated to an algebra of bounded operators. And so from the algebra of bounded operators, you can certainly consider unbounded operators. It's all fairly complicated, but just I mean, it's extremely well known that working with unbounded operators has many technical difficulties, and often if you can show that your unbounded operator is affiliated with bounded operators, and affiliated basically meaning that it can be approximated in a useful way by bounded operators, and that you can deal with the unbounded operators through that mechanism. I don't know whether that answers your question.
Yeah, thank you.
Let me add that this is a very famous theory developed by Voronovich, right? Who explains of how you can actually generate a sister algebra by unbounded operators. And his
Yes.
motivation was working on quantum AX plus B groups. I mean, when you are looking simply at algebra, you know, with usual stuff A and B, that's fine for you. But these guys are not only that you go into a non-compact group, but the problem is that what is naturally algebraically generating this non-compact group is unbounded. And this is when Voronovich developed this whole theory of how you can generate sister algebras by unbounded operators. So there's the whole very subtle theory about unbounded operators generating sister algebras. But this is like a completely separate lecture. Okay, any other, okay, I have something on chat. I was wondering, a student talks, oh no, this is old. No, sorry, there's one new. Could you share this presentation with us? Yeah, it will be uploaded. It will be uploaded. So Mark, please correct the 2 typos you found yourself and send the corrected version to the baby steps. Okay, I have one more question from Zoom. Go ahead. Sakib.
Yeah, hello. So I have rather not naive technical questions. So we started in the commutative case with compact space, but so little Guilford-Neymark theorem, it also gives us the equivalence of categories when we have locally compact spaces, and we take the commutative sister algebras to be compactly supported continuous functions on that space. So my question is, like, while defining the metric using the Lipschitz constant, like, is there any technicality while going from compact to locally compact Hausdorff, or like it goes like it's true in that case also?
Well, there are, yes, lots of technicalities that are important. I mean, the very first one being that if you look at the probability measures on your non-compact space, and look at, well, they are not, the set of probability measures is not even closed for the weak star topology, and in particular, it's not at all compact. It's, in fact, it's a somewhat weird space, and so already from that gives you many difficulties in trying to figure out what a non-compact quantum metric space should be. And my former doctoral student Frédéric Lettre-Molière has written several papers about that, but that's basically a direction in which much more work is needed to be done to really sort out how to deal with the non-compact situation.
Okay, anybody else? Anybody else going once? Go ahead.
I have a question about the definition of this compact quantum metric space, but it's like a vague question. So what was your motivation for this definition? Because I guess it wasn't just to generalize, right, metric spaces.
That's right. I was motivated by various examples, and also by I looked quite a bit at the high energy physics literature, which I encourage everybody. This is theoretical high energy on the archive, and I definitely don't understand most of it, but I take the stance that I'm reading it like poetry and saying what ideas it causes to appear in my head. And I began seeing statements of the following kind. You have a sequence of matrix algebras of increasing dimension, and this sequence of matrix algebras converges to the two-sphere. No definite, I mean, as is typical with physicists, they don't give precise definitions, and then they gave no definition of converges. And I said to myself, what on earth could this possibly mean? And from looking carefully at the kinds of calculations they were doing, they were with this idea, they were keeping track of lengths very carefully in their calculations. And I said to myself, this seems to be that they're somehow using metric ideas. And so maybe there's some way to make these matrix algebras into some kind of non-commutative metric space, and to show that then the sequence of these algebras does indeed converge to the two-sphere with its usual metric. And one of the puzzlements was that they would say in other places, well, we have this sequence of matrix algebras of increasing dimension, and that converges to a projective space. You know, and how could the sequence be converging to the two-sphere, but also converging to a projective space, and things like that. But anyway, I was able to sort all of that out and make sense of it exactly by using this definition of compact quantum metric spaces and the appropriate non-commutative Gromov-Hausdorff distance between them. So that was one of my main motivations. But there are all sorts of things that are being done and said in the high energy theoretical physics literature that I think can offer all sorts of interesting problems for mathematicians to try to make sense of it.
Okay, we have 8 minutes till final cutoff, and there is a question here in chat. Marc, can you read the chat? Or should I read it out for you?
Please read it out.
Okay. You have interpreted a compact metric space XD in terms of ALD, which is purely sister algebraic, more precisely a non-commutative one. In the same spirit, I have following question. Suppose you have a Riemannian manifold MG. There is, in addition to the distance, there are several mathematical quantities, for instance, curvature. Is there any sister algebraic interpretation of that one?
There are certainly papers in the literature dealing with curvature for certain classes of non-commutative C-star metric spaces, if you want. I mean, usually where you have a Dirac operator, in fact, and Alain Kahn himself has contributed to some of these papers, but there at the present point there's no general theory, but theory is being slowly developed. It seems to be quite complicated, but definitely very interesting and important to do.
Okay, Adam.
Yes, I have the following question. Since you mentioned this deformation quantization, and your approach to this business of deformation quantization is via the so-called strict deformation quantization, where you really work in the C-star algebraic setting, and everything is defined very precisely. But there is also this approach of Kontsevich, which is purely formal. And I wonder, what is your perspective on your approach versus this Kontsevich approach and the relation with physics? Which one should be more appropriate?
Kontsevich's definition is purely algebraic and much broader in scope, and deals with many examples that I and other people don't know how to deal with in the C-star setting. But on the other hand, I mean, I'm not well informed about his work, but as far as I know, it doesn't tie in very directly with quantum physics, in the sense that it usually doesn't have Hilbert spaces and operators and states and observables and things like that. So I this may be partly my ignorance. Are you aware of any apparatus like that, Hilbert spaces and states and so on, that occur in Kontsevich's work?
No.
I think
So
Kontsevich is mostly about Poisson geometry, right?
Yes, that's right. So which of course, ordinary Poisson geometry is very important in physics, but yeah, I don't yeah, classical physics. Yes, I don't see how his work ties in directly with quantum physics.
Okay, thank you.
All right. We have 3 minutes left. So anybody else going once? Anybody else going twice? Anybody else from the Zoom? Okay, let's thank Marc again for a very, very exciting talk. So
Thank you very much. My pleasure.
Thank you, Marc.